welcome to Classical Mechanics 2. In this video, we'll learn about geodesics. In the last video, the toy problem I posed to introduce the calculus of variations was find the shortest path between 2 points in a plane. But what happens when the surface you're trying to find straight lines along is curved? Imagine that I want to take a flight from Atlanta to Sydney, Australia. I can't take a path that follows a straight line in Euclidean space. This would involve drilling a tunnel through the center of the Earth. Given that I'm confined to live on the surface of the Earth, what path has the shortest distance between Atlanta and Sydney? Here's a potential flight path. Currently, there are no direct flights, but if there were one, it would likely take a flight path similar to this one. This flight path lies along a line that's called a great circle. This is a path that passes through antipodal or opposite points on the surface of a sphere. It's the largest circle you can have on a sphere. The equator is an example of such a great circle. It isn't a straight line in Euclidean space, but it's the straightest line you can get on the surface of a sphere. Lines like these are called geodesics. Sometimes the surface isn't as symmetric as the sphere. For example, if I were hiking and I want to go from this lake here to my car parked at this lake over here, the path that the crow flies follows a line that looks like this. But depending on the height of the mountains, this might not be the shortest path back home. It might look something more like this. This would be the path that got me back home in the fewest total steps. But I could pick a different metric I want to minimize, for example, the shortest time from when I leave to when I get home. This is actually what happens with light. Imagine it's a beautiful spring day and we're sitting by the side of the lake. There are some fish jumping out of the water, and we notice that there's a slight distortion in their image as they leave the water. To track down what's happening, we want to know what happens when a photon leaves the sun and goes into the lake. A light ray comes into the air-water interface at angle alpha and leaves it at angle beta. Air and water have two different indices of refraction. Fermat's principle, or the principle of least time, states that a path taken by a light ray between 2 points is the path that can be traversed in the least time. Snell's law is a solution to Fermat's principle where there is an interface between two materials with two different indices of refraction. Snell's law states that the index of refraction of air times the sine of the incident angle is equal to the index of refraction of water times the sine of the angle that it leaves the interface. Here's a material which has slabs of width delta x with linearly decreasing indices of refraction. If I were to send a light ray into this medium, it would follow this trajectory here. It turns out that Fermat's principle gives us a solution to this that is identical to the brachistochrone. Given a ball that's falling under gravity along some path from point A to point B, the brachistochrone is the shape that minimizes the time it takes the ball to get from the top to the bottom. In fact, all mirages are the result of bending light rays. This is an image captured by Simone Engels of what appears to be an enormous iceberg in Vancouver Bay. It turns out that this is actually a superior mirage, which occurs when there's an inversion layer in the atmosphere. This is a rare event where a layer of warm air traps a layer of cold air under it. The difference in density of the layers of air causes the light rays to refract. Instead of going back out into the atmosphere, light rays bend down to ground level. This image is actually showing Mount Shim, which is more than 200 miles away. Fermat's principle extends well beyond the scale of desktop ray optics. It extends to the cosmologic scale as well. The theory of general relativity is based on the idea that massive objects distort both space and time, and yet Fermat's principle holds here as well. The shortest distance between point A and point B in a spacetime, which is a geodesic of that spacetime, is also the quickest path a light ray can take. This is an interactive simulation by my colleague Steve Treadle. What's going on here is that every pixel in the view screen is the origin of a light ray that gets sent out into the gravitational field caused by this Schwarzschild black hole here. As light rays travel away from the screen, they're being bent by the curvature of spacetime around the black hole. When a photon hits an object in that scene, we render it. Sometimes a light ray never hits an object, like the light rays that fall into the event horizon here. This is a place where light rays can never escape the pull of a black hole. This simulation has an Earth-Moon system orbiting the black hole. The dynamic motion helps us visualize the distortion coming from the gravitational field. As the Earth and Moon pass in front of the black hole, everything appears as they would in Euclidean space. But when they pass behind the black hole, we see something really interesting. What we see is the Earth and Moon break up into concentric rings around the event horizon. What's going on with those rings? To find out, let's look at this other simulation by Steve Treadle. This is modeling an accretion disk around the black hole. An accretion disk is formed when a spinning cloud of dust and gas interacts with the gravitational field of a massive object. Instead of forming a sphere, like our atmosphere, it forms a disk, like the plane of the orbits of the planets in our solar system. This is an accretion disk around the equator of our black hole. The camera is moving up and down towards the north and south poles in this simulation. Let's start by looking at the top half of the accretion disk. If this were Euclidean space, the back of the disk would be occluded from view, like Saturn's rings. But here the gravitational field makes it look like it's being stretched out towards the North Pole. Likewise, the bottom of the accretion disk appears beneath the black hole. This is exactly what happened in the Earth-Moon system in the previous simulation. The bits of the Earth or Moon above the equator got mapped above the North Pole, and the bits below the equator were visible below the South Pole, creating a ring-shaped mirage. This is one way to see behind a massive object. This phenomenon is known as gravitational lensing, which describes the way photonic images are distorted in the neighborhood of a strong gravitational field. Cosmologists use this to study very distant objects that might have been occluded by massive galaxies. This distortion enables cosmologists to see multiple copies of objects behind the massive object. For example, here we see 2 copies of the accretion disk, but we might see 4 copies of an object obscured by an elliptic galaxy. That motif is called the Einstein cross. Additionally, these images take very different amounts of time to reach a faraway observer on Earth. The difference in time that it takes for the images to arrive enables cosmologists to study the temporal dynamics of the distant system. Steve's shaders are available for you to play with. They work on Chrome and Firefox browsers, and I'll link to them in the description below. In the next video, we'll work out a special functional that we can use to solve for the dynamics of mechanical systems. This functional is called the Lagrangian. Thanks for watching, and I'll see you next time.